Hi, this is Miss Slitton, and this is 7th period filled with wonderful honors bio students. Say hi. Hi. All right, so we are going to attack chapter 2. First thing, things like understanding what matter, anything that takes up mass, takes up space. We got that down. We learned states of matter, solid, liquid, gas, plasmas. Most of the universe is what? Plasmas. Excellent. We started looking at the periodic table and the organization, right? What did we call the vertical columns? Groups. What did we call the horizontal? Periods. Right. Okay. And we'll review how they're set up in just a minute. I just introducing that. We looked at chnops, which is 95% of our body weight, consists of these elements. Let's say them together. Ready? Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. Okay, good. All right. Did you have to look at that in your POGL on organic molecules? Did you look to see what each one has? What does a hydrocarbon contain? Hydrogen and carbon. Good. All right, just checking. Then we started talking about the atom. Let's review the atom story. Here we go. The atom story. Atoms are made of protons, neutrons, and electrons. The protons and the neutrons are in the nucleus, atomic mass. The electrons are in energy levels, 2, 8, 8 and 32. 8 is great. Octet rule. Perfect. We will mop it. Now, can I vary the number of protons? No. If I vary the number of protons, I'm varying the what?
Element.
Yeah, I'm changing the element. Can I vary the number of neutrons?
Yes.
Yes. What is it called when you vary the number of neutrons? What is it called? Isotopes. Isotopes is when you vary the number of neutrons. When you vary the number of neutrons, what else will it impact? The atomic mass. Yes.
Oh, wait,
Now it's working? Are you good? Is there something you want me to repeat because the Wi-Fi was down for a moment? Okay. Can you vary the number of protons? Yes or no? No. Can you vary the number of neutrons? Yes. What's it called? What else will be impacted by that? Atomic mass, because it's a factor of the protons plus the neutrons. Can you vary the number of electrons? Yes. What is that called? An ion. Now, does the number of electrons in the outermost energy level determine the behavior of an atom? Yes. Atoms always want to get happy. 2 ways to get happy. What are the 2 ways? We can fill up our outermost energy level. That's a great way to be happy. In fact, we know ones that do that. What are those called? The noble gases. They're the ones on the periodic table who do not need to hook up with any other element to be happy because their outermost energy level is full. Helium is the first one because helium has 2 electrons total and the first energy level holds how many? 2. Happy. Okay? Second way to get happy is to have what? 8 valence electrons. Hence the name what? Octet rule. Hence the name octet rule. Perfect. All right, so when we look at something like lithium happy, yes or no? No, lithium is not happy. Let's talk about lithium. This 7 right here represents the what? Atomic mass. Good. And the atomic mass consists of what 2 things? Protons plus neutrons. So if I'm going, is it 3.5 protons and 3.5 neutrons to get it to 7? No. How could I figure it out? Yeah, that number right there is protons. And that is referred to as the what? Atomic number. Can we ever change the atomic number? No, we're changing the element. So if the mass is protons plus neutrons and you subtract off the number of protons, I'm left with neutrons. In this case, how many? 4. Okay? Ask your bio buddy. You got any problems with that?
A lot of them, but I'm not going to say it.
All right, next. Let's put those electrons away that we have. Focus, try to be here, okay? Because you have a quiz tomorrow, okay? How many electrons do you have? How many electrons? Below. How many? 3 electrons. So how many can we put in the first? I'm going to have to do a tour group just for 10. Can you give me just a minute? Okay, we're going to pause just a minute. Okay, I'm back to the recording. Back to the recording. Come back to me. Okay, so let's give. Where is Sparkle? The 3 electrons, let's give them a home. How many can we put in the first energy level? 2. How many do we have left? 1. Where are we going to put that?
The second energy.
Okay, is lithium happy?
No.
What might he do? Give it away electron. Exactly. If he gives away that electron, what will he become? He'll be a positive charge. What will he be attracted to? Negative charge. Thank you for letting them do that. I'm the first tour stop every time. So
That's cool.
That means
You're the best.
yeah.
okay. Yeah. All right. Now, we did that. We did that. We did that. I'm moving on. We already did that. Okay. Let's get into bonding. Okay, come back to me. We talked about 3 kinds of bonding. Ionic bonding, then what else? Covalent bonding and hydrogen bonding. So ionic bonding has to do with ions. Okay, so oops, I skipped it. Coming back here, okay. So here we can see ionic bonding is when you have something that has given up an electron, maybe it has a positive charge. Something else to get happy gains an electron. Okay, so it's a negative charge and opposites attract. Okay, so that's an ionic bond. A full transfer of at least 1 electron. Okay, and it's attraction of oppositely charged ions. Covalent bonds are different. Nobody's giving anything up. In covalent bonds, what are you doing? Sharing. And when you share in pairs. Good. Pairs of electron. And every pair is called a what? Bond. So if you have a single bond, you're sharing 1 pair. If you have a double bond, you're sharing 2 pairs. Does all sharing, is it always fair? No. When it is unfair, when somebody has a stronger pull on the shared electrons than another, that's called a covalent bond. Polar covalent bond. What is a perfect example of a polar molecule that has 2 polar covalent bonds in it? Water. Yeah, water. Because oxygen shares electrons with hydrogen. Hydrogen shares electrons with oxygen, but it doesn't share fair. Oxygen has a stronger pull on those electrons than hydrogen. So oxygen becomes partially what? Negative. And the hydrogens become partially positive. Then, because of that polarity of water, you put a whole bunch of water molecules together. They're going to arrange themselves so that the partial negatives are hooking up with the partial positives. But they're not sharing any electrons, it's just the partial. So what kind of bonds do we call those? Hydrogen bonds. Okay, so those are your 3 bonds. Ionic bonds, complete transfer. Okay? Polar covalent bond is you're sharing, but somebody's got them a little bit more. So polar covalent bonds can lead to hydrogen bonds. Okay? When they share perfectly fair, what's that called? Nonpolar. Nonpolar covalent bonds, all the electrons are shared evenly. Nobody has a charge. If nobody has a charge, it's hard to associate with water. So that makes you hydrophobic. But if you have a molecule that has a charge on it, or it's a polar molecule, partial charge, or an ionic bond, that would be hydrophilic, because water can arrange itself around it. Okay, check with your bio buddy and see how they're feeling about that so far.
So partial charge,
I understand this.
when things are polar covalent stuff, one has a positive, one arrange one together.
Okay. Come back to me. Go ahead.
Oh, never mind, you're doing it right.
Okay, so here are several water molecules, and within each water molecule are 2 polar covalent bonds, right? Because oxygen has got a stronger pull on the electrons they're sharing. So he is partially negative, the hydrogens are partially positive. Those right there are sharing electrons, unfair, that's a polar covalent bond. As a result of that, you have some partial charges on water molecules. And you have a whole bunch of water molecules with all of their partial charges. So an oxygen's partial negative charge is going to be attracted to a different water molecule's partial positive. There are no hydrogen bonds within a water molecule, right? The only kind of bonds within a water molecule are what kind of bonds? Polar, covalent. Within a water molecule. Within a glass of water, you have what kind of bonds? Between each of the water molecules, right? Remember, when water sticks to water, what is it called? It starts with a C. Cohesion. So if I had water between my fingers, like this, and I made a little water bridge between my fingers because they're all hanging on to each other, that is a result of cohesion. Okay? When the water attaches to some other surface that's polar, that's called what? Starts with an A. Adhesion. When water evaporates out open stomata, do you remember what that was called? Transpiration. And that's due to that cohesion and adhesion, yeah? Okay? When you jump in your pool like this, belly flop, they all hang on to each other, right? And that's called what? When the edge of the water, where the water meets the atmosphere, what is that called? Surface tension. Perfect. Surface tension. Good. We talked about water because of all these hydrogen bonds. They can hold a lot of heat energy. So as the sun shines down, these hydrogen bonds are like, I can take it, I can take it, I can take it. That's why water has a high heat capacity. And also it has a high heat of vaporization. It takes a lot of energy before it will vaporize back into the air because the hydrogen bonds are all hanging on to each other. Remember, oxygen is a gas and hydrogen is a gas, but when they're together, they are a liquid. So we looked at those different properties of water. It's a liquid instead of a gas. It's a good solvent if what? It's because it's not a good solvent for everything. If you're charged or you're a polar molecule, if you're charged or it's a polar molecule, then you're a good solvent because those things are hydrophilic. You're not a good solvent if you're hydrophobic. If you have a lot of hydrocarbons, what's something that would be hydrophobic? Oils, fats, lipids, right? Because there are a bunch of carbons sharing with a bunch of hydrogens, and they're sharing very fair, so they are hydrophobic. Gains heat, high heat capacity, loses heat slowly, high heat of vaporization, and then a key one we talked about that ice is, there's surface tension, there's this, good solvent. We said ice is less dense, even though it's a solid, it's less dense than liquid water. And why is it? Because as the molecules have less kinetic energy and they slow down as they're freezing, they create equal space for all their hydrogen bonds. And that equal space in there makes it less dense. Whereas liquid water, they can be, close and changing around. And so it is more dense. Equal space, ice floats. Which is good for lakes because it keeps life alive. Okay, next, we talked about pH. So key things about pH is that it's a measurement. You talk about it being a negative log. You're not going to need to memorize that, of the number of hydrogen ions. Okay, so you're measuring hydrogen ions. If you have a low pH, means you are acidic if you have a low pH. What can you tell me about the hydrogen ions if you're acidic? Yeah, you have a high amount of hydrogen ions. If you're basic, you have a low amount of hydrogen ions. Okay? Now, if you're not a hydrogen ion, what would be the other one related to pH? Hydroxide, OH minus. So where you have high hydrogen ions, you have low hydroxide ions, OH minus. Where you have low hydrogen ions, you have these, a lot of hydroxide ions. What we need to remember is every time we change a level in our pH, it's really what? 10 times. So let's say it was a solution was supposed to be neutral, but I made it instead a 4. So you're like 4, 5, 6, 7, no big whoop, right? But no, you're going to say it is a big whoop because 7 to 6 is how many times? 10. 6 to 5 is how many times? 10. 5 to 4 is how many times? 10. 10 times 10 is 100 times 10 is 1,000. So a pH of 4 is 1,000 times more acidic than a pH of 7. And a pH of 3 would then be 10,000 times more acidic. A pH of 2 would be 100,000 times more acidic. Do you see how that keeps? We just keep multiplying it out. Okay? All right. Buffers help keep whatever solution you want, help keep it that particular pH by either absorbing hydrogen ions or hydroxide ions. Okay, that's it for the chemistry. Now, organic. Now, what's going to help you the most with your organic molecules? Your debrief. Yeah, that debrief. You made a good debrief. It's going to be awesome. Okay? Because you need to know, first of all the organic molecules contain what? Carbon. Okay? And the exception is carbon dioxide because it's so simple. Now, the simplest thing you can add on to carbon is what? And then you would have a hydrocarbon, right? And we looked at different kinds of hydrocarbons, and we know we burn some of those as fuel. Okay? We talked about how to go from monomers to polymers, and then we can do the reverse too, going from polymers to what? Monomers. What is the name of the reaction by which you join two monomers together? Dehydration synthesis. Not only will you get your polymer, but what other molecule will you get? H2O. Because you're combining things, so you don't need as much stuff anymore. Think about it like that. You've got to take something away so you can hook them together. Okay? So we've dehydrated the molecule. What's another name for that reaction? Condensation synthesis. The opposite. If we want to go from a polymer into monomers, we need to add in what? H2O, water. Okay, and what is that called? Hydrolysis. Perfect. These types of reactions require something to make them happen. They're not going to spontaneously happen at a speed that we can live with. So what is that called? Enzymes. Enzymes facilitate both dehydration synthesis and hydrolysis. It's not going to just happen magically. You have to have something there. So we wanted to know that because we wanted to know the 4 important organic molecules: carbohydrates, lipids, proteins, and nucleic acids. By the way, I posted like 3 quizzes in the stream in Google Classroom to help you review these. Okay, 3 different ones. One's on water, one's on chemistry, one's on just the organic molecules. I think a couple of those in quizzes. So you have a lot of practice questions. I put them in the stream. Okay, so look in the stream. Okay, so these are your 4 important organic molecules. You need to know the functions of these as polymers, but you also need to know the monomers that build them. And the good thing is we use the same reactions to build them all. Okay, so the monomers are like bricks to build the wall of the polymers. The only one that's kind of weird, what's the weird one that doesn't work like exactly? Lipids. Okay, that's the only one that's kind of weird. Okay, so let's go through that. So the monomer, the brick for carbohydrates is always what? Sugar. And if we boil sugar down to its simplest chemical formula, do you remember what we found out? It's C what? H2O. Okay, so this is C6H12O6. If we wanted to simplify that, right, we could divide everything by 6. Are you with me on this? And then it's just what? CH2O, which is why we say carbohydrate. Okay? Okay? Now, if you want to make a disaccharide, what would be the reaction to go from the monosaccharide of glucose and fructose to make the disaccharide sucrose? What's the name of that reaction? Dehydration synthesis. What's another name for that? Condensation synthesis. Perfect. Okay? And we looked at the 3 disaccharides. All of them have in common what molecule? They all have glucose. Okay? Hook a glucose with a glucose, and you have maltose. A glucose with a fructose, you have sucrose, table sugar. Hook a glucose with a galactose, and you have lactose, milk sugar. Those are all your disaccharides. Your polysaccharides, they have stuff in common. They don't dissolve well in water, which means they're hydrophobic. Okay? They're too large to pass through a cell membranes. Some are used for energy and some are used for structure. The energy ones, do you remember the two energy ones? Glycogen in animals, we put it in our liver usually. Glycogen, do you know the other one? Starch. Who makes starch? Plants. Okay? Those are polysaccharides. Oh, okay. Those are polysaccharides that are used for energy. Do you remember the ones that are used for structure? Chitin. Okay, what is chitin used for? It's fungal cell walls and the exoskeletons of insects. Okay, what was the other one? Cellulose. What is cellulose used for? Plant cell walls. Okay, those are your carbohydrates. So when we look at our review that we did in our debrief, we had the monomer. This was our symbol for the monomer. We said here are the three common monomers, glucose, fructose, and galactose. These are our disaccharides. Here are our polymers, and starch and glycogen are energy, and cellulose and chitin are structural. And that was our review. Okay, moving on. Let's do the weird one, lipids. Lipids umbrella has two categories, fats and steroids. Fats are made out of glycerol and 3 fatty acid chains. Those fatty acid chains are really long, right? And we talked about those fatty acid chains have 2 states they could be in. What are the 2 states for those fatty acid chains? Saturated and unsaturated. Okay? Saturated. Guys, can you put chairs up as you're leaving just for me? Guys, not now, but when you leave. Okay? Saturated and unsaturated. Saturated means you're saturated with hydrogens. The white balls in here are hydrogens. And when you have all these single bonds, okay, all these single bonds, they stack well, and they become a what at room temperature? Solid at room temperature. Okay, a solid at room temperature. What kind of fats are saturated fats? Animal fats. Animal fats are saturated. Unsaturated fats means that carbon has some double bonds in it. And as a result of that, it is not saturated with hydrogen. Some hydrogens are missing because they have a double bond right here. And as a result of that, the double bond, that grouping of electrons, causes a little kink in your chain. And when you have a kink in your chain, it makes you a what at room temperature? Liquid. And we can see that when we look right here. We can see the unsaturated, it's not easy to stack, saturated is. We talked about a modification. Did you want that picture again, sweetheart? Is that what it looked like you got your phone out? There we go. Yes?
So what determines whether it makes a double bond or whether it uses the hydrogen bond?
Oh, it's just animals tend to make those saturated fats and plants make the unsaturated. It just is. You don't have to like the why. We won't answer the why. They do. Okay. We can propose a lot of things. Now, the other thing we need to talk about is a modification of this right here is removing one of the chains and replacing it with a phosphate group, and it's called a phospholipid. It's a major component of cell membranes because it's 2 rows of phospholipids. These long fatty acid chains are going to be hydrophobic. The phosphate with the phosphorus and the oxygen around it is going to be hydrophilic. And it's facing the watery interior of the cell or the watery exterior of the cell. Okay? Another lipid besides fats is what? What's the other category? We said fats and steroids. So here are your steroids. Steroids are made out of, instead of long fatty acid chains, hook them together and make a what? Ring. And there are always 4 rings together when you have steroids. All steroids ultimately come from cholesterol, a modification of cholesterol. Steroids. Steroid hormones like testosterone, what else? Estrogen and progesterone. Good. All right. And so when we talked about lipids, we said our monomers were 2 options. We could have, for fats, we have glycerol and fatty acid chains. and they could be saturated or unsaturated. We know plant and animal on that. Steroids, we have 4 rings, 4 carbon rings. Polymers, fats and oils, that's for energy. You know that. Fats are for energy. Phospholipids are in cell membranes. Steroids build cholesterol, hormones, and waxes could be for waterproofing. So just through that, it's another lipid. All right, this brings us to our third important organic molecule with multiple functions within our body, and that is proteins. And all proteins are ultimately built out of what? Amino acids. So amino acids have a central carbon. They have a hydrogen, a carboxyl, an amino group, and an R group. How many different R groups are out there? 20. Biggest worry I have is you've got to remember that amino acids build what? Proteins. Not, what am I afraid of?
Carbohydrates.
Nucleic.
I'm afraid you're going to say nucleic acids. You're going to pair up the 2 acids. Don't do that. The acids don't go together. Then you have a mess. Okay? So don't put any acids together. They're going to explode in your face. Okay? All right? Amino acids build what? Proteins. Amino acids build proteins. And there are 20 different amino acids because there are 20 different R groups that you could have. And we said they fold into certain shapes, and their shapes are very important for their function. Okay? And then we said you could cook a protein, you could denature it, right? You could denature it. And when you denature it, it could be permanently denatured, like if you fried your hair, right? Or you fried an egg. Or it could be temporarily denatured due to temperature and pH. We're going to learn that later. Okay? So then when we do our reminder for proteins, our debrief, we have the monomer. We know this is the amino group, the H, the carboxyl group, the variable. I think I would add on to this one right here. I would add on to your debrief. I would have done 20X because there's 20 options on that R group. That's like celebrity status when you're all like... Okay, polymer, the functions, I just listed off. They're like all throughout your body. So I think you'll remember what proteins are used for. Okay, last but not least are nucleic acids. Nucleic acids, you had 3. What are the 3? DNA, RNA, ATP. Okay? DNA is your genetic code. RNA you use to build proteins, and ATP, energy. They all are built out of nucleotides. Nucleotides build nucleic acids. Nucleotides consist of 3 things: a base, a sugar, and what? Phosphate. Okay? All right, nucleotides build nucleic acid. What is a nucleotide? A base, a sugar, and a phosphate group. How many different bases do we have? 5. Okay. Adenine, thymine, guanine, cytosine, and uracil. Now the part that switches out is uracil and thymine. Thymine. Okay. Thymine. Okay. It's because it's black.
Yeah, that's orange.
Oh. Okay. Sorry, my bad. Thymine. Thymine is in DNA, whereas uracil is in RNA. The sugars are different. What are the 2 kinds of sugars? Ribose and deoxyribose. Who gets ribose? RNA. Who gets deoxyribose? DNA. And the phosphate is the same. Yes?
I didn't catch what the G meant.
Oh, adenine, thymine, guanine, and cytosine. If you want to see, yeah, actually. They are, here's deoxyribose and ribose. Okay? And then here are your different bases. Cytosine, thymine, uracil, remember those were the pyrimidines that only had 1 ring. And then adenine and guanines are the purines. Okay, tell me this. Riddle me this. Could I have a nucleotide like this in DNA? Let me tell you about this nucleotide. Adenine, deoxyribose, and phosphate. Could I have that in DNA? Adenine, deoxyribose, and phosphate. What do you think? Yes or no? Is adenine found in DNA? Yes. So that's a yes. Is the deoxyribose found in DNA? Yes. Is phosphate found? Yes. So could I have that in DNA? Yes. Could I also have it in RNA? No. Why couldn't I have it in RNA? You have to have a ribose, right? You with me on that? Okay. Where could I have this? Where could I have this? Thymine, ribose, phosphate. No.
Thymine isn't in RNA.
It's in neither one of them. Thymine is only in what? DNA. Ribose is only in RNA, and then they both have phosphate. You see that? See how I did that? Okay. If you understand that, then you will get any question like that right. Okay? RNA is single-stranded, just a long chain of nucleotides, where DNA is what? Double-stranded. Double-stranded. Okay? DNA is double-stranded, and what holds the two strands together? Hydrogen bonds. Perfect. Hydrogen bonds. And then the last one you have is ATP, stands for adenosine triphosphate, right? And it has adenine and ribose and phosphate, phosphate, phosphate. When you break off that last phosphate, you get energy. That's why it's the energy currency of our bodies. And I have really good review questions for you to do embedded in here. But before I do that, let's do this. Here's the monomer. Phosphate, sugar, base, and I listed off bases there. What do I not have right here? Uracil. Oh, whoops, sorry. And that's found where? RNA. Okay. And then I talked about the polymers and then ATP. If you want to stick around, these are questions I would likely use in a quiz if you want to try to do it. Yes?
What should we be?
Oh, be creative.
Ooh, yes.
Be creative. Okay, I'm going to start it right away so people can do it. Okay, so be creative. All right, I'm going to start. Okay, guys, there are 16 great questions here, so try to do them. Okay, 16 great questions. Okay, and for those of you at home, I'm going to show you the questions. Here's question 1. Pause it if you need to. Question 2. This is question 2. This is question 3. Question 4. Question 5. Question 6. And this is 7. Here is 8. Here is question 9. Question 10. Question 11. 12. This is question 12. Question 13. Question 14. And question 15. And question 16. And then I would remind you to do your additional objectives as well. I'm going to pause you for a minute to give people a chance to respond. Okay, we're going to go ahead and resume and check our answers now. So, question number 1, amino acids build proteins. Looks like all of you got it right because these are just extra names. Good job. 4 rings of carbon build lipids. dash what? Steroids. Remember, 4 rings of carbon. Okay? Number 3, sugars like glucose build carbohydrates, not proteins, right? Sugars don't build proteins or fats. Now, if you have excess sugar, will you convert it into fat? Yes. But sugars like glucose build carbohydrates. You can hold a water droplet between 2 fingers held slightly apart. This is due to cohesion. Everybody but one of you got that. It is not a balance between hydrogen and hydroxide ions. Yes, nucleotides build nucleic acids. Perfect. Saturated fats are a solid at room temperature and come from plants. What makes this statement false? What should we say? Comes from animals. Yeah. Number 7, a chemical reactivity of an atom is dependent on the number of electrons in its outermost energy level. That's what determines its behavior. We better discuss this because exactly 0 people got it right. Okay, so let's talk about it. When you do dehydration synthesis using 2 amino acids, you will form a protein. Yes. Amino acids build proteins. Amino acids, you will form a water molecule. Yes, because what is it called? Dehydration synthesis. So water is generated because you take an H and an OH. Fatty acids and glycerol, will you form a nucleic acid? No. What do you build when you have fatty acids and glycerol? You form a fat, specifically a lipid. Okay? Polymers form monomers. No, what is it? Monomers form polymers. Nucleotides to form a nucleic acid? Yes, and then that one was just because. Okay, it's not loud. Number 9, an example of hydrolysis is breaking a starch into a glucose. It is not building lipids from fatty acids and glycerol. Okay? When you think hydrolysis, do you think build or break? Break. You think break. So it has to be one of these 2 breaking down. Do you break down glucose into starch? No, you break down starch into glucose. Number 10, which of the following would be in DNA? Thymine, because it's only in DNA. Phosphate, both. Deoxyribose is found in DNA. What's wrong with A? What's wrong with B?
Uracil.
Uracil is not going to be hooked up with deoxyribose. Good job. Number 11, when you do hydrolysis to a fat, you get fatty acids and glycerol. You do not get sugars. You do not get nucleic acids. You don't get water because you consume water, right? You have to put water into that, and you don't get oils. 4 of you got it right. Good job. Which of the following is a DNA nucleotide? Definitely E. What's wrong with A? Uracil. What's wrong with B? Ribose. What's wrong with C? Well, what's wrong with C? Because both of these would be found in RNA, and I asked what's found in DNA. Good. And D, what's wrong with D? Good. 13, hydrogen bonds are found between the slightly positive hydrogen of one and a slightly negative oxygen of another. That is true. Okay, an example of a dehydration reaction would be building lipids from fatty acids and glycerol. Why couldn't you say A? You don't build amino acids from proteins. You build proteins from amino acids. Do you see that? Okay, what's wrong with C? Dehydration reaction is a building reaction, so you don't pick any one of these breaking. Okay, because it's about a building reaction. Number 15, hydrogen bonds form between hydrogens and oxygen of a single water molecule. No. What's inside a single water molecule? Only polar covalent bonds. Perfect. And then number 16, yes. Ions are atoms that have gained or lost electrons. Good job. Way to do it. I'm proud of you. Can you help me put up my chairs before you leave? Yeah. Please, thank you.
Look at my to-do
Have a
list.
good evening. Make
What?
good choices. You are loved.
Model paper.